This is going to be kind of the opposite of what everyone else is going to do because I became aware of artificial intelligence in the 1960s. And so I'm going to tell you some things about 1960s era artificial intelligence. Not really, because actually I've had the benefit of 50 years of extra confusion to add on top of the confusion that existed in the 1960s. Back then there was a figure named Marvin Minsky who thought that the thing that you could do with computers was, since they were logic devices, you could teach them how to think logically because, of course, thought is a logical process, right? By the 80s, when I was a grad student, people realized very well that thought has nothing to do with logic. All right, cool. And in fact, trying to teach computers how to think logically, as in expert systems and whatnot, is not going to get you anything approaching human thought. They still use the term artificial intelligence, which I love using today because one cannot use that term without a certain level of, or a layer of irony. But at any rate, by the 80s, Marvin Minsky, who was already in the scene in the 1960s, I believe, was saying that he was surprised by a thing, which is this. The things which started being called perceptrons, and I think the term perceptron is even older than Minsky, but Minsky and Papert might have made the idea of a perceptron famous, right, in the 70s? I don't know. Back when I was a kid. At any rate, the thing about a perceptron is it doesn't think any better than a logical system thinks. But on the other hand, it's a thing that is differentiable, or actually, even less than that, it's a thing that is continuous, a continuous function of what you do with it, which is not the case of a logical transaction. And so you could hope to solve optimization problems. And the big surprise, which I think the name associated with is Rumelhart in the 80s, is that you can make this thing called a multi-level perceptron, which is a fanciful idea of what a neuron might be. And maybe it's worth delving into that for a second or two later. And you can actually optimize the puppy. And the way you optimize it is by using the thing which I hadn't heard before the 1980s, which is called backpropagation, right? So here, what the picture would be is this. Sorry, this is going to be the opposite of everyone else's talk because you're not going to see any slides. You'll see some patches, I hope, if they work, or if they don't work, I'll still show them to you. And the thing I want to emphasize is is more on a, whatever you say, foundational level of what we're actually trying to do when we make these machine learning systems, right? And of course, today you're not supposed to say artificial intelligence, you're just supposed to say machine learning, or even data analysis or data science, because that sounds like you're being more honest. And my answer to that is perhaps, but on the other hand, I like the irony of using artificial intelligence, so I still use that term. So what you're going to get is about 40 minutes worth of irony, unless you stop me with questions, in which case I will redouble the irony. All right, so here, I'm going to start with a caveat, and this is a thing a math teacher told me in the 70s, I think, which is this. I'm going to start with an example, and then I'll proceed to the punchline. So let's make a unit square. Let's inscribe 4 circles in it. Sorry, I'm drawing with a mouse, which I should never do. And then let's inscribe a little teeny circle in the middle of that, right? Okay, that's a thing, right? Okay, this is high school level math, right? So now let's do this using solid geometry. So we'll go up 1 dimension, so everyone knows where this is going. It's going to be about dimensionality. So we'll make a cube now, a unit cube. And we're going to, I can't draw this very well, but we're going to pack it with 8 spheres, all right? And then, now I'm going to change colors here, how about that? Then we're going to put a tiny little sphere inscribed in the 8 little spheres. Each of them, if it's a unit cube, each of these 8 spheres has a diameter of 1/2, and this tiny thing has an area which is a tiny fraction of the area of the cube, right? Now let's go up to a mere 10 dimensions, which is a small dimensionality in machine learning, whatever you say. And then a funny thing happens, which is that by the time you hit dimension 10, this little tiny sphere inside this cube actually reaches outside the cube. Okay, the punchline being, you think you know about geometry, but when you start getting above about 4 or 5 dimensions, your intuition about geometry is useless, right? And in fact, you can, I'll even show you that this is true. I'm sorry, this will take 30 seconds or so. So here, what the question is, really, is what is the radius of this sphere, and is that bigger than this segment, which has length 1/2? So what's the radius of this sphere? Well, of course, it's the following. To get the radius of the sphere, we draw a segment out to the middle of this sphere, and then we subtract 1/4, which is the radius of that sphere, because the diameter is 1/2, right? So it's just, so this distance here, which is the radius of the sphere, is the distance out here minus 1/4. The distance out here is 1/4 times the square root of n, where n is the distance, right? Sorry, is the dimensionality. So we'll just say subtract another 1/4 like that. Square root of n is 3.2-ish, square root of 10, right? And of course, that means that this is about, I'm doing this wrong. Oh yeah, this is about 3, this is a little bit bigger than 2, and 1/4 of a little bit bigger than 2 is bigger than 1/2, and this green segment is longer than that blue segment. Ouch, right? Any questions about this? Someone ask a question, come on. No? All right, oh, well, now, okay, fine. Well, let's make ourselves a nice little autoencoder, right? Autoencoder means we'll put in 1,000,000 pixels, right? And then we'll just squash it down to this tiny dimensionality, which is 512. And then we'll go back and generate our image again, right? That's what an autoencoder looks like. And what are on both sides there are going to be backprop, learnable, multi-level perceptron hoo-has, right? And now try, and then, of course, all you have to do is just navigate in this nice little 500-dimensional space, which is tiny, right? And, right, it is not tiny. It is far too big for you to believe you know anything about it whatsoever. And that is merely 512 dimensions as opposed to the 1,000,000 dimensions that you started with, which is the space of all possible images, say, right? So, so what do we do when we do machine learning? What we do is we do things at random, in the hopes that our intuition is telling us something, but in the certainty that our intuition probably is telling us something that is 180 degrees away from the truth. Oh, not 180 degrees away from the truth, because, by the way, if you throw 2 vectors out in a high-dimensional space, the average angle is not 90 degrees between them, right? No, it's very close to 180 degrees, and so on like that. Everything you know is wrong, right? Just don't even try to think correctly about this stuff, because you can't. All you can do is stab around and do stuff and see if it works or not, which is precisely what people have been doing with this deep learning stuff for the last 10 years, as far as I've been able to tell. And I won't give you any evidence for that. I'll just let you see if you agree or not over time. Questions about this? Right. 512 dimensions. By the way, how close are we to filling a nice cube of 512 dimensions if we throw 1,000,000 points at it? Well, or all right, I'll be generous, 1 billion points, right? Let's just, entire music catalog of the world, let's throw it in there and see how big it is in a 512-dimensional unit cube. Forget it, right? So then you have this problem. I'm telling you why this is never going to work, right? I'm going to try to scroll now. Yeah. Okay, so now what we're doing is something like this. So I'm going to give you, okay, so in 2 dimensions, okay, so here's the thing that people do a lot, and it's kind of fun, right? So we're going to mess with timbre space. Now, the simplest possible approach to timbre space might be something like this. I want to have an instrument which has 2 inputs. I'm going to give it an amplitude and a frequency, a pitch. And I want it to make a nice saxophone sound at that amplitude and pitch. Right? I'm not going to be able to play you my beautiful saxophone sound, by the way, because I don't have sound. But I'll tell you, you didn't have to hear it. It's going to be terrible. Okay, so problem. when people play high notes on saxophones, actually saxophone is not the worst example of this, but you can't just play every possible dynamic at every possible pitch. At certain pitches, you have a very restricted kind of dynamic range. And it might be that at low pitch, okay, so if pitch is here and dynamic is here, so piano to forte, right? Then it might be that your quiet note, that your low notes are all kind of quiet and your high notes are mostly kind of loud, right? Like that, right? And now I'm going to say, well, cool, I'm going to now give it a bunch of data, which is some saxophone player is playing a nice sax solo that I'm going to train this thing from. And what does that look like? Well, it looks like a path that goes wiggling around as the saxophone gets quieter and louder and goes up and down, right? And and it's worse than that because every time the saxophonist takes a breath, you get one of these, right? But that's all right. We can do things about that, no problem. And now the thing that we're going to do is hook this up to a keyboard, and the first thing we're going to do is say, well, what about middle C at the very quietest possible dynamic? There it is. So here's middle C at the very loud. Okay, so now we're asking the thing to extrapolate. We're not asking it to interpolate at all, right? And why do people use sigmoid-ish so-called artificial neurons to extrapolate functions, right? Oh, okay, and now, remember, we're doing this in 512 dimensions, not 2 dimensions, right? So the truth is much, much worse than what I'm telling you. The truth is actually unimaginably bad, because almost no matter what we give it to try to do, it's going to be doing something that isn't anywhere near the convex hull of the spaces of the points that we gave it to learn on, right? So what we're asking it to do, almost without, what's the right word? Unavoidably, is we're giving it a segment of stuff to learn on, and we're asking, and we're telling it what is true about that segment, and then we're asking it what is true about some point that's outside of that segment, right? Where this is where horizontal is the input and vertical is the desired output, right? And I don't know if you guys did this too, but I decided when I was a kid that all I had to do to get rich was to go to the library, pick up the Dow Industrial Average as it went from day to day, record that or write that down for about a year, which is only, 200 or so trading days, right? And then I'll just make a polynomial that goes through those 200 points, and then I'll just extrapolate, right? And then I'll know whether the thing's going to go up or down, and then I'll get rich, right? I don't know, have any of you tried this? You should have. Well, okay, you need a computer. Well, okay, the punchline is it doesn't work. You probably already know this. In fact, there are people getting rich on Wall Street telling other people that they can do it who can't, right? So in fact, I was solving the wrong problem. I should have said I knew how to do it instead of realizing that I didn't know how to do it. And that also is an interesting object lesson for us all. Now, yeah, I told you I wasn't going to give you any positive results, right? Okay, so let's, so how do brains do this? So going back to Minsky in the 60s, computers, they're hardware, they can do things like simulate stuff. What if we just simulated a human brain and just figured out how the human brain does these creative things that clearly the current state of machine learning is completely unable to do, right? By the way, it's not completely unable to do it. People get it to do things. They just never know why they're getting it to do it, and they never can do it twice on successive days and get the same result. But that's, okay. That doesn't mean it's useless. That actually might, for instance, when you're cooking an omelet, you get exactly the same thing. You never know what you're going to get, but you always get something, right? And usually you can eat it, right? So it's not a necessary condition that we do this, that it be predictable or understandable in any way. But at the same time, somehow you have this intuition that if you could understand what was going on, you could do it a little better, right? And it's clear that we could be doing a lot of these things a little bit better, like not making cats with 5 legs and stuff like that, right? So All right, well, let's do this. Oh, I'm sorry. Let me fill in one promise that I made about something I was going to talk about. So the thing is this. Okay, multi-level perceptrons. What that is you get a thing which is a neuron, which I'm going to put in scare quotes, right? And the neuron does something very simple, which is it simply multiplies all of its inputs by various gains. And then, sorry, I have to draw a bit bigger box. After it's made the weighted sum of these things, then it applies this thing called a sigmoid function, which is a saturating function, which does this, right? And then that's your output. And then the multi-level perceptron, okay, that might be an artificial neuron, or it might be called a perceptron, which is, I think, 1960s language for what this thing is, right? A multi-level perceptron, MLP, is just a bunch of these things. Whoops. Oh, no, go away. I want to do that, okay. A bunch of these things arranged in layers, typically, with some sort of connectivity. For instance, the simplest thing, of course, is just to make it fully connected, right? And then each one of these things has coefficients that you have to give it, which are the gains that you put on all the inputs that might be positive or negative. And then what you've got to do is optimize the function. Right? Ah! That's the rub, okay. The easy thing turned out to be how to optimize the function. The hard thing, as we all found out in the next 30 years, was that we didn't know what function we were trying to optimize. So the real thing that you do when you're doing machine learning a la multi-level perceptrons is someone is giving you a bunch of examples, and what you are going to do, how do I get this thing to go away? Sorry. My web browser is throwing me a piece of information, and it is showing up on the wrong screen. Okay, here we go. Okay, so what we're going to do now is we're going to say, look at this nice MLP that I've got. It's got a whole bunch of parameters. So what it really looks like is it's a black box, and it's got parameters coming in, and it's got inputs. And anyway, we also know that the inputs actually correspond to reality actually gave us some outputs out. And furthermore, the MLP gives us outs. Maybe I'm supposed to put a hat over that, I'm not sure. And now what we're going to do is we're going to subtract these, and okay, that's going to be a big minus. And then we're going to try to minimize this. Right? Okay, and now the big hidden assumption here. This difference, by the way, is not a one-dimensional quantity. It's not a number. It is a number for every possible input that we're going to train this thing on. So it's a billion numbers, perhaps, right? Because we're going to have a billion examples we're going to train this thing on, right? So what we're really going to minimize is a billion tuplet of errors, each of which is what? Well, it is how far our prediction is from the truth. And that requires a measure of distance. Now, and I'm sorry, do you all know about the problems about distance in large numbers of dimensions? There's a Wikipedia page that has some title about the tragedy of multidimensionality. The tragedy of multidimensionality is if you throw a whole bunch of points down in a million-dimensional space, they're all about the same distance from each other. There's no structure at all that is given to you by the notion of distance. But that's not the worst thing. The worst thing is that we don't even know what distance is when we're talking about audio, because we don't know how different, we have no way of measuring how different one piece of music is from another. Right? We can sort of say, yeah, we'll just take spectral envelopes of time snapshots and call that the distance, but that is not at all, well, that's an approximation of distance which will get us somewhere close to what we're trying to do, but will never get us exactly what we're trying to get to do because it's not really the difference in two percepts, right? The next problem, if you think a billion dimensions is bad, how high dimensional is the human brain? So what is a percept? A percept is maybe a special case of a mental state, right? A middle state is the state of every neuron in your brain. There are about 1 trillion neurons in your brain. Each one has about 1,000 axons popping into it. So we're talking a quadrillion, a million million connections, each of which, all right, so, each of which is running at a sample rate of maybe a couple, call it 1,000. You're clocking about 1 kilohertz, right? So we're talking 10 to the 15th operations per second. Right? And furthermore, we're not just going to run this program for a second or a minute or a week like we would machine learning example. We're going to run it for our entire lifetime, because that's the amount of time we have in order to do our own little bit of machine learning up here, right? So what we find is that there might be between 5 and 10 orders of magnitude, or maybe 15, between what we can get out of the server farm up by the hydroelectric dam in Alaska that Google is using, right? And what we can just do inside our brains for 100 watts. That's the power budget of your brain. You need 2,000 calories to live through a day. Most of it is going to your brain most of the time because you're asleep and stuff. But if you divide it out, it's 100 watts. It's about twice what my laptop is using. And it is about 10 to the 10th faster, or more powerful, I should say, right? So maybe there's a future in wetware that somehow exceeds what we can imagine doing with silicon ever in the foreseeable future. Okay, so so this idea of machine learning being being modeled on the human brain is pulling a little bit of a fast one, because in fact the human brain is so much more powerful than our computer that we would never be able to do anything like what it does, or even like what an ant does, and ant. And furthermore, it's wrong anyway, because the thing about our neurons is they don't act like this at all. Like this, I mean, I'm trying to point at this thing and failing, but you know, this thing, the perceptron, is not like your neuron. Your neuron is clocked, and it has memory, but it also has a pulse, and what comes into it is not values, it is pulses, it's time signals. And what it does depends on the chemical bath that it's sitting in, as well as the relative timing of whatever is whacking into it on its inputs, in a way that's far more complicated and probably far more interesting than anything that our so-called artificial neurons can do. Sorry, I'm just telling you all why you shouldn't be doing machine learning, right? Or, to put it in a positive light, I'm showing you how brilliant these people are who actually get results out of machine learning, despite the fact that we are facing such awful limitations in what we're able to do. Now, differentiability, just because that's the topic of this last couple of years. Differentiability is about trying to make this optimization problem better. By the way, this minimization problem is ill-defined, so what we're trying to do already is probably wrong, but let's do it anyway. And now what we get is the following situation. Okay, so how do you minimize a function? Right? Okay, so first, all right, so here's a nice function, and I'm going to try to find the minimum. This function is the error function, which is over maybe a billion-dimensional space, because there might be a billion coefficients for our artificial neural network that we need to train, right? Okay, and of course, what you do is so suppose, just for simplicity's sake, suppose we're just talking about y equals x squared, right? So what we're going to do is we're going to proceed by gradient descent, which means that we're going to, at whatever point we're at, we'll work iteratively, and we'll figure, okay, look, which way is down from there, and then we'll go in that direction, right? And so, okay, so if we start at point number 1, now what we're going to do is say, well, okay, so my first attempt is 1. What's my second attempt going to be? Well, it's going to be 1 plus, and what it's going to be 1 plus is the derivative of this thing, which is 2x. Oh, I guess I should subtract, and then I'm going to multiply that by some negative gain, right? In fact, obviously the negative gain should be 1, shouldn't it? So then, right? Shouldn't you just multiply the slope downward by 1, just go one step in the direction that you want to go? Well, if you do that, your x2 is going to be -1. You're going to have overshot the minimum by 100%. And then if you repeat the process, you'll get back to where you started. And better than that, obviously that's not converging fast enough. We're just going 1 minus 1, 1 minus forever. Let's just increase the gain to 2, right? All right, then you get 1 minus 3 plus, I don't know what, exponential, right? And then the thing blows up, and then we have to start over, right? Oh, sorry, we have to drop the gain. Let's drop it to 1/2. And then you get a great result. If you say, oh, my gain is going to be a half, we'll get 1 plus 2 times minus 1/2. Went straight to 0. No problem, right? So obviously 1/2 is the right number. Now, let's merely push this up to 2 dimensions and see what happens. In 2 dimensions, I'm trying to figure out how to scroll now. Okay, there we go. So in 2 dimensions, and sorry, I can't draw this very well, but here's an attempt at drawing a paraboloid which has one dimension along which it doesn't wiggle a whole lot, and another dimension along which it does. All right? So there's a paraboloid with a presumed minimum here, and we're going to be somewhere out here. And our gradient descent is going to get us real fast down here, and then is going to take forever to work our way over there, right? Now, just imagine this was 1 billion dimensions, and consider what the ratio might be between the biggest slope and the smallest slope. And you might understand that you might have a great deal of difficulty making your way down to the minimum, right? Because, of course, by the time you get down here, you're going to say, well, yeah, the reason we weren't moving very fast was because that gain that I talked about was too low, right? We have to push the gain up. But if you push the gain up, what it's going to do is it's going to start wiggling you back in this direction until it blows up again. So you're in trouble. Now, okay, so now you can take probably a semester-long course at Stanford or MIT and learn how to improve this situation. But the basic deal is you have to fiddle with it. And of course, really, oh, it's time for me. Any questions? I got 7 minutes for questions. Sorry, I'm trying to provoke you guys, and you're not provocable. Really? Okay. Everyone is just enjoying listening to me.
What is it useful for?
What is it useful for?
Yeah.
Well, all right. Okay, good. I got 7 minutes. Let's see. I'm going to show you something that's really cool, but I'm not going to be able to play you what it sounds like just yet. Where's my thing? Ah! Okay. This is probably going to fail because it's failing. Oh, I didn't initialize. Okay. Now the thing is, all right, okay, good. I'll do this from the beginning. This is an idea. This is an idea due to Sam Pluta, who is a computer musician who graduated from Columbia 10 years ago, maybe, and has been working with the Wet Ink Ensemble, making as their electronic musician ensemble member, which is kind of a cool idea to be one of. And among many other things, he has developed a patch in Super Collider, I believe, that has a few hundred parameters that does all kinds of stuff. And he gets himself a tablet with about 4 different screens on it, and he wiggles stuff around with his fingers and gets through this big parameter space. And now the thing is, well, okay, what if he wanted to be able to get through the parameter space quickly without having to switch screens and move 50 pots so that he can get from one nice sound that he knows how to make to another? And the answer is, well, let's use machine learning to do this. Okay, this is an abuse of the whole idea of machine learning, right? Because what he's going to do is he's going to find 5 or 6 presets that's to say 5 or 6 sets of parameters that he can load into his super collider nonsense, his madness there. That's got granular synthesis and some FM and some this and some that. It's got all, and feedback, you know, all kinds of stuff, right? And so all you got to do is just find a bunch of good sounds and teach a machine learning algorithm what kinds of sounds you like it to make by teaching it what kinds of parameter sets are kind of cool, right? So here is, in this afternoon I'll get to where you can download this and then you can try it yourselves and see if this is any good for what you want to do. So this is my distillation of this idea down to additive synthesis. So here what you would do, and I'm not going to show you how to train it because I don't want to spend any more time than I've already spent. But here's a joystick. It's not really a joystick because I don't have one, but I'm just pretending, right? And of course I can't have 2 joysticks because I've only got 1 mouse, right? But what I did was I gave it 5 training points, 4 corners in the center, and for each one of them I gave it an additive synthesis instrument amplitude set. So all I've got is a Hammond organ style patch. It has 10 drawbars, and I can just move the drawbars up and down, right? Not as a function of pitch, just straight up single presets. And now, one thing that I thought I wanted to be able to do was just have a quiet, like everybody's at 0, you just shut up thing. So I put that up here. And then I just gave it 4 fanciful timbres, right? Here's a kind of an odd harmonic, computer music clarinet imitation kind of a sound. Here's a nice bright sound that's mostly the upper harmonics. Here's a sort of reasonable diapason kind of a sound. Here, I forget what I put. It doesn't seem to, there might not be anything there. I don't think there is. And then what you do is you get your machine, you get your neural network package out, and there's one for, I mean, there's a neural net package for everything now. This is a port of what do we call it? It's the package called FAN, the Fast Artificial Neural Network, which is, I think, 20 years old. Imported into PD by, I've forgotten his name. Daniele, I'm sorry, I can't get his name anymore. I'll find it this afternoon. But anyway, there is a PD FAN package out there, which I have brought up to date and I'm using for fun. And so what I've done is just taught it with these 4 examples, interesting synthesis parameters that I can now quickly move between using only 2 parameters of input, right? Cool. Now, this is a total abuse of everything that you are going to be seeing in the rest of the day, right? Because this is a training set of 4. In fact, the way Pluto uses it is even worse because he has 2 joysticks, which means he's got 4 dimensions, which is already, as I've shown you, impossible to imagine. And he is training it with between 4 and 6 points. So he takes his joysticks and he slams them both northeast, and he puts a sound on that, and he does that like between 4 and 6 times, not exaggerating, right? And then he just trains a neural net on this using some Python package, I don't know, and out comes a synthesizer that he can play. Go figure. Well, it's no more absurd than anything else I've seen anyone do with these things. I mean, you know, this is a 4-dimensional absurdity as opposed to a 1,000-dimensional absurdity. It's no less absurd, and it's useful. So I guess that's a positive note I can end on, which is you actually can do stuff that's cool, but you shouldn't imagine that you're doing anything that is predictable or correct in any sense. On the other hand, music doesn't have to be correct. You know, theorems have to be correct. Music has to have some other quality which is not a truth value. It's not the case that Mozart K500 and whatnot is true and Bach B something or other is false or something. No, that's not how music works. And so you can do things like this in a musical context and have it be truly useful for reasons that no one will ever really understand. But nonetheless, it doesn't make it an uninteresting thing to play around in and not necessarily something that can't be very productive for workers to dabble in. The musicians even. All right, and I think I have to stop, so I'll stop because it's time.